Welcome to Data Science Part 3. So, the first thing we're going to do, as in every single class, is we're going to have to stay fresh with the material. So, does someone want to walk me through the steps of getting up to date on the latest GitHub material from SF-15? Yes, Catherine from, where are you from? New York? Where's New York?
Westchester.
Like Scarsdale? Is it Scarsdale High School? Okay. I know things. Catherine from Scarsdale. How do we get fresh material from GitHub? What do we do?
So I think you're already there, but
How do I know?
you do LS to see if you...
I could LS, but there could be other folders with the same exact stuff in it. How could I be sure that I'm in the right folder name? PWD. PWD will at least tell me the directory that I'm in, and I can recognize Dropbox, Teaching, GA, SF-15. Yes, that's where my repository is. Now, how do I get the freshest material? Well, we've already cloned it, right? We've cloned it once, and you never have to clone it again, unless there's some gaping error in the system. We've already cloned it once, but there's another P command. Exactly. Not git push, we're going to git pull. So if we git pull, mine will say already up to date, because I own it and I made it up to date. But when you do git pull, you will see words and the matrix have it right in front of you.
I have a question.
Yes.
So when I do git pull, let's say there is a zip file on the repository and in my folder, and if I have modified the version in my drive, do they get over it?
Good question. Short answer is no. The question was, if you make changes locally and I pull, will it overwrite my changes? Short answer is no, because what I'm making sure of doing is I'm not changing anything that I put to GitHub after we've gone over it in class. So that when you pull, Git is looking for only files that have changed, that I've changed. And because I'm not changing those files, it's not going to try to overwrite it. To be safe, longer answer, to be safe, if you want to make sure that just in case something happens, you can put all of your .p, whatever you want, you can put all of your files in your own SF-15 work and save it there if you want to keep like a second copy of it. But the short answer is no. When you do a git pull, it should not overwrite anything that you've done.
But then, an extension of that question, if you do make changes, it will overwrite what I have.
If I make changes, then yes. But I have done this enough times to know that I'm just not going to change any of them after class has started. If I want to make revisions, like, oh, I fixed typos, I will make a literal new file called the same name, -revised. And then when you pull, you'll just have a new file there. Yeah, so I'm being very careful as to not change anything so that no one's file work gets overwritten. But if you do want to be safe, you can always copy them over to your own, wherever you want, to have a second copy. If you're having problems with the git pull, please don't hesitate to raise your hand and have a TA come help make sure that it is all up to date. Because, as always, if the git pull doesn't work, you're not up to date. Let me see a show of hands whose git pull worked. Awesome, awesome. You didn't get like an error like, hey, merge conflict, or hey, blah, blah, blah. Also, guys, TAs and students alike, obviously the conversation during the class is absolutely fine. But it does get a little bit loud, at least for me, and I imagine for other students between. So if we could try to keep the conversations at a dull roar, that'd be awesome. Just because I got some comments that it's a little loud when we talk. So let's try to keep it a little quiet, and I will try to do the same by doing the exact opposite by being louder, which you can imagine hard to do at this point. Okay, so the first thing we're going to do on our GitHub, on our agenda, is we're going to look at the slides for the data science workflow. So if you go ahead and open up, it's in your slides folder in your SF-15. There's a new slide called 03_intro_2_DS data science. So this is a brief 30 to 45 minute presentation on the introduction to data science, including some examples of what data science problems look like. And the purpose of this is to get you not only thinking about what data scientists are and what they do, but also part of your thought experiment homework is to start thinking of actual ideas for your project. And hopefully the examples here and the examples that are on the GitHub will prove to give you some idea of what types of problems that you might want to tackle. So the agenda for this slide, what is a data scientist? Who are we? We're not just dudes in hoodies. We have feelings. How data scientists add value to both society and to the workplace. The actual data science workflow, which is comparable to the scientific method from school, if you remember, and some qualities of a good data scientist. So, what is a data scientist? And I want to hear, what are your definitions? So this is probably something you've heard about, maybe in a news article, maybe you've heard it at work, maybe you've heard DJ Patel talk about it. Does anyone know who DJ Patel is? Who's DJ Patel, Danielle? I can't hear you, I'm sorry. Say it again? Not quite. You got... Yes, he is the first ever in the history of America, or slash the world, the first ever chief data scientist of the United States government. That position did not exist before DJ Patel took it less than a year ago. DJ Patel is a fantastic man. He has many free ebooks online. He's actually got his PhD from the University of Maryland in mathematics and computer science, so that's why he's my hero. And so you might have heard someone like DJ Patel talk about data science. He used to work at LinkedIn. He did all the LinkedIn data work. So what are some of your definitions of a data scientist? Be as crude or as specific as you'd like. What is a data scientist? Someone raise your hand and tell me. What's a data scientist? Let's go back to the say your name loudly, just in case, because I still feel like not everyone knows each other's names. So say your name loudly and then tell me, what is a data scientist?
My name is Sam.
Sam, what is a data scientist?
I would say a data scientist is someone who takes large amounts of data and tries to understand patterns or insight that it could expose.
Patterns, insight. Define large.
More than a gigabyte.
More than a gigabyte. Wow, that's a lot of data. More than a gigabyte. Okay, someone else? Say name and tell me.
My name is Nancy.
Nancy, tell me.
I think for data scientist, this person knows more statistics than an engineer, but knows more programming than a statistic.
Okay, so I'm hearing statistics, engineering, insight, patterns. Someone else? How about this side of the room? I'm only looking at this side of the room. What is the data scientist? Don't make me do this. Braden?
Uses programming to go through data and expose insights.
The truth.
Yeah.
Okay, programming, engineering, statistics, patterns, insight. I like all those words. There is one thing that I will mention, and that's the large. You have large data sets. To me, a data scientist is someone who extracts knowledge from data, period. That is a one-sentence definition that I hold. It is not the tell-all, end-all definition. It is someone who extracts knowledge from data. Whether that's through programming, through statistics, through pattern recognition, those are all parts of data science. But if someone can take in a data set, whether it's over a gigabyte in size or over only 150 rows, like in a World Health Organization data set that we're going to look at, made by the government, whether it's 150 rows or 10 million rows, the data scientists can take in the data. They have the programming knowledge and the statistics knowledge to not only read in the data, but read the statistics. And they're able to generate insights in pattern recognition. So I think all of those put together makes a very good definition of a data scientist. Here's another one. A data scientist is a data analyst who lives in California. This joke is much funnier in Maryland, where people are like, Californians, they compost everything. So I still don't understand. I can't compost. I don't get it. I realize I'm breaking the law, but this makes a good distinction. What is the difference between a data scientist and a data analyst? Because a data analyst, that position has existed for decades. You can go back job descriptions for decades and see the word data analyst. What is a data scientist that makes it so different? What do you think? Name and...
Oh, sorry. Nick.
Nick?
I think essentially two factors. One, there's actually more of a programming engineering component where some data scientists will create algorithms or engines of some kind, and then the other is applying statistics or other more academic needs to analyze data.
Do You mean the data analyst is more academic? Is that what you're saying?
No, data scientist is more.
Oh, data scientist. Okay. So what's the difference between that and data analyst?
Simpler, using simpler math, say analyze data or Excel, just some simpler tools.
Okay. Okay. Did you have your hand up?
Sure. Why not?
Name and tell us.
Name and what?
Name and then tell us.
Oh, hi. I'm Sean,
Sean.
and I think there's more of a BI component to data analysts.
Business intelligence, I assume. Yes. Okay. There's a business intelligence component. How so?
A lot of the data analysts I've worked with have been much more focused on being able to generate reports and, I guess, shallower insights from the data.
Okay.
So simple segmentation.
Okay. Okay. Catherine. I mean, name and tell us.
Catherine.
Catherine.
And I think that my opinion is that data analysts usually, because they're very close to BI, they don't have to do as much data mining coming up with their own data, where a data scientist is responsible for aggregating their own data.
Mm-hmm. So I'm hearing data scientists focus on data mining a lot more of the time, collecting data, cleaning data. Whereas data analyst might be more on the, I have the pre-cleaned data, now I can generate insights, business intelligence. And how does the data scientist do all of this? By using more programming, by using more academic means, like Nick was talking about. So I think that those are actually pretty good definitions between data scientist and data analyst. Now at Data Assembly, we have data science course, and we also have the analysis course. Analysis tries to be more like data analyst type class. We're in the data analysis class, what we focus a lot more on is how to ask the right questions. So it's a very BI, business intelligence type of problem. Is how do we boil this down into the most specific and simple question possible, and then how do we use the data to answer that question? Obviously, data scientists do this as well, but the tools that a data scientist has at their disposal are much more on the programming, machine learning, and advanced statistics and academics and linear algebra. To kind of go what I think Nancy said this, a data scientist is someone who's better at statistics than any software engineer and better at software engineering than any statistician. What this tweet is trying to make light of is the fact that data scientists are not only good programmers, but they're very good at statistics and math. To put that in a more succinct way, data scientists solve complex problems using data mining techniques. And there's this pretty little Venn diagram here that shows kind of the three sides of the data scientist. You might have seen this graph before, but I'll explain it a little bit further. The three sides of a data scientist are the computer science side, the statistics side, and the problem domain. Now, you probably are very familiar with computer science and statistics, or at least knowledge of what they are. Computer science being the knowledge of using Python and Spider and IPython notebooks, potentially using R, Julia, Scala, some other languages as well. But this is the programming. This is how do we actually bring in data into a programming language. Statistics is understanding histograms, understanding charts, understanding what is the mean versus the median, what is standard deviation, how do we normalize data. This is how the statistics knowledge comes in to better understand what we're looking at. Now, problem domain. Does anyone want to take an educated guess at what do I mean by the problem domain? Yes, name and tell us.
Desiree.
Desiree?
So the problem domain would be expertise or experience in whatever question you're trying to ask.
I think that's a perfect definition. Problem domain is expertise in whatever field that you're trying to do data science in. So for example, data scientists exist in the medical field, data scientists exist in healthcare, data scientists exist in education, data scientists exist in banks, at financial institutions, non-financial institutions, non-profits, for-profits, NFL, NBA. Data scientists exist, well there should be more in NBA and NFL. Data scientists exist in many fields. So they have to be knowledgeable not only in programming and statistics, but also in their field. If someone comes up to me and asks me to do a data science problem in medicine, I will be able, I went to Johns Hopkins, but I'm like the 2% that did not become a doctor. I don't know much about medicine. In fact, I know pretty much nothing about medicine. So when that happens, I have to call up a friend who knows more about medicine than I do to get some of the problem domain. So a data scientist is knowledgeable in at least one of these three areas. Now, because there's such a wide variance in skill sets between how to program, how to do statistics, and sports or medicine or whatever domain you're in. Because of that, many job descriptions are more appropriate for a team of data scientists. Maybe one data scientist is the programmer, one data scientist is the statistician, one data scientist is a sports analyst and has been for 20 years. So more often than not, a data scientist job could be split up into 3, give or take, positions. Now, if you are an amazing data scientist, you have knowledge in all 3 of these. But what I just said, having knowledge in all 3 of these, problem, computer science, statistics, problem domain, that causes an issue. Because that implies that I'm very knowledgeable about one problem domain. So those who choose to zone in or hone in on all 3 of these tend to get stuck in a field. Whereas most data scientists find value in moving from problem domain to problem domain. Again, that's not to say that you should not stay in one problem domain if that's what you want to do. But one of the caveats of trying to be a master of all 3 is that we tend to get stuck. For example, if you tend to hone in on computer science, what may end up happening is you may get stuck in a language. You might get stuck in Python. You might get stuck in Java because you spent so long working on it. If you spend your life focusing on statistics, you might get stuck there. I only know lambda calculus. I only understand this type of math, and it's hard for me to move around. Likewise, if you hone in on the problem domain, crap, I'm a doctor. Well, it's not that, but you get the point. So, as data scientists, we must find the balance of all 3 of these things. So how do data scientists add value to the workplace and to society? Well, data mining techniques generally add value in one of the following, that should say 3 things. 3 things. Number 1, predicting the bad. And we'll see examples. Predicting the bad. Number 2, identifying the good. Sounds like pattern recognition. And number 3, automating existing processes. This is not the exhaustive list of how data scientists add value, but most use cases of data scientists can be thought of as one or more of these 3 things. Identifying the bad, predicting the bad, identifying the good, and automating existing processes. Now, automation sounds like that's not a data science problem. That's more of that's like a programmer's job. That's a software engineer's job. On some levels, yes, but the data scientist must be aware of the process, the statistics behind the process, and the best way to emulate that process. So all 3 of these are very good examples of data science attributes. So data science can be found within many fields, and I have a few examples to kind of motivate the rest of the course. And also, I took these from this YouTube video down here. Feel free to watch it. You have the link on your slides. Predicting neonatal infection. The problem is that children who are born prematurely are at a very high risk of developing infections, many of which are not detected until after the baby is actually sick. So obviously the problem here is that children develop neonatal infection. That's obviously a problem. But one of the bigger problems as doctors is identifying neonatal disease or infections. Because more often than not, the doctor can't tell until the baby actually starts developing symptoms of that infection. So the goal is, can we detect subtle patterns in the data to predict the infection before it occurs? So of those 3 items, which one of these, on the previous slide, of these 3 ways of adding value, which way are we adding value? Predicting the bad. So in this case, we're trying to predict neonatal infection. Why? For the purpose of treating the infection at an early stage to have better hopes of curing it or maintaining it or whatever it is, however you can handle the infection. So, that's the problem and the goal. Does that make sense? Any questions? Does anyone think this is not a problem? Good. Okay. Data. 16 vital signs of the child. Heart rate, blood pressure, respiration rate, all kinds of simple medical data points of the child, taken every blank minutes, blank hours, blank days. This model was able to predict the onset of infections 24 hours before the child actually developed any of these symptoms. And you might be saying, hey, Simon, that's great example, and it's nice to think about, but this is real. This is actually an actual data project that was done, and I put a link to it at the bottom. This is an actual data science experiment that someone performed and succeeded. They were actually able to identify the neonatal infection 24 hours in advance to ordinary symptoms appearing. So this is an example of trying to predict the bad based off of these 16 vital signs: heart rate, respiration rate, blood pressure, so on and so forth. That's an example of data science. Here's another one: automating government paper pushing. My sister works in the government, so she's keen on this one. The problem is processing disability claims at Social Security Administration is a very time-intensive process. Many claims take over 2 years to actually go through the system. Whether or not they're approved or not, it takes 2 years to even go through whatever process that they have at the government. It's a very long time to wait when you have a disability claim. The goal is to automate the approval of some of the simplest disability claims. What is simplest? Well, that can be something ranging from, this is an easy yes or an easy no. So the goal is can we create software that could predict yes or no at a very high accuracy rate? What's the point? Are we trying to replace all the humans? No, we're not trying to replace all the humans. What we're trying to do is we're trying to give the easy ones to the computer so that the humans have more time to work on the harder ones. The ones where they have to work with the person one-on-one to figure out what they can do. So it's just giving the humans more time to interact with each other while the computer takes care of the very easy ones. Do they have insurance? Is it minor? Are they healthy? Otherwise, yes, give it to them. That process, which could have normally taken weeks, was now boiled down to seconds. So it just gives more time to human-on-human interaction. That's the real goal. That's the underlying goal. The data is just text. The data is an application that somebody fills out. It's just words, which is likely one of the most unstructured pieces of data that you'll ever work with is text. And we will spend a few days working with a lot of text. So the data here is words. So rows, there's no columns, it's just however many words this person decided to write down on their application. The impact, again, this is real. The impact was they were able to fully automate 20% of those claims. So 20% of those claims were handled by a computer on off hours, not by a human. Human never had to look at 20% of those claims. Leaving the humans to work with the remaining 80%. You might be saying, oh, hey, 20% is not very high. Fine, fair enough. But 20% of how many disability claims coming in every year is a lot of disability claims being handled without human intervention. And that's not enough for them. The rating accuracy, if you didn't know, government claims are rated by a third-party service. Their ratings accuracy were actually better than the average claims officer. So this computer was not only doing all the work for the human, but it was doing it better. It was doing it faster, and it was getting a higher rating from that third-party system. Is that a question? Sorry. Oh, okay. All right. So those are two examples of data science. Predicting the bad, and what is this one? Automating an existing process. Also, potentially, identifying the good. So picking out what makes a good claim, and then one that's able to be answered as yes, or approved. But mostly this is automating an existing process. So how do we do these problems? Those are all great one-slide examples. But how do we, bless you, how do we go from a problem to a solution just like that? And there are 5 steps to do so. Step 0, which I like starting at 0 because, why? Because Python is 0 indexed, like most languages. And we are now 0 indexed. Number 0, i.e. the first one, is defining the problem and question. This seems simple, but if you mess this one up, if I mess this one up, if you mess this one up, if Ramesh messes this up, the remainder of the analysis becomes extremely difficult. Not impossible, extremely difficult. Because if we can't ask the right question, we're going to get halfway through and say, I don't even remember what I'm trying to do. I don't even remember what the point of this was. I don't even know if I care about this problem. So defining the problem in question is so key. It might take as little as 5 seconds. It might take days to think about. But for example, in the first example, can I predict infection before it occurs? That is a very simple question. You can make it even more specific. Can I predict infection 24 hours in advance? Can I predict infection 36 hours in advance? Can I predict infection 48 hours in advance? There are many ways of asking very similar questions. And the data scientist must be aware of how to iterate on questions if one of them doesn't happen to pan out. But this question, can I predict infection before it occurs, is very specific enough. For example, a non-specific question for this same exact problem would be, can we predict infant mortality rate? Which sounds like a specific question, but when you think about what goes into that question, we have to now follow this child throughout months. We now have to look at more signs. We now have to look at many more things, and that will become more difficult down the road. So this is a question that is specific, it is time-oriented, there is a clear answer, yes or no, and it's a good question for data science. The second one, can I predict claim approval from the start of the process? Again, this is a simple yes or no question. That's not to say that yes or no questions are the best questions, but they happen to be the simplest of questions. Yes or no, true or false. You could ask a question such as, okay, on a scale of 1 to 5, how much do I think that this claim will be approved? 5 being absolutely, 1 being not so much, and there's a scale. You can extend that scale from 0 to 100. So there are many ways of asking a similar question, but this is a very simple one. Yes or no, will it be approved? Any questions on defining the problem in question? Once you've defined your problem in your question, it's time to identify and collect the data. For the first one, it's the heart rate, the blood pressure, the respiration rate, all of those data points must be collected and identified and collected. This is where the problem domain becomes very important. Because knowledge of the problem domain makes it much easier to identify and collect data. If someone asked me to predict neonatal infection right now, I would be at a loss because I don't know what are important infant vital signs and have to consult a doctor about that. So this is where the problem domain becomes very important. For the second example, that data from the application with mostly free text, there's my identifying and collecting data. So it's a little easier in the second one because that's all I'm given is free text. In the first one, I actually had to think about, well, I have a child here in front of me. What are the vital signs that I would like to look at? So I have to make that conscious choice of which signs do I monitor. Whereas in the second example, I was given an application, and that's the end of the story. That's my data. Exploring and preparing. This is actually where we'll be starting today with Pandas. Exploring and preparing data. And for your homework and for your thought experiment, I will ask you to begin thinking about steps 0 and 1, the thinking of a problem and identifying the data. Today, we're going to actually look at how do we explore the data once we've collected it. That's what Pandas is very useful for. So, for example, for the first one, maybe you want to aggregate the data at the minute level. Well, why would we do that? It's probably already in a nice format. Well, let me ask you a question. Has anyone here ever worked in a hospital? Or with a nurse or a doctor or some kind of medical field? Well, you're lucky, because let me tell you, you know who's collecting this data? Guess. Who's collecting this data about children? Nurses are way too busy. No, they don't have time for this. They have way more important things to do. Who is it? Interns, undergraduates at the nearby college, unpaid people. There are people who should not be in charge of collecting data. Again, going to Johns Hopkins, most of my roommates were doing this for no money just to get into medical school. The problem is they're unmotivated and they don't really know what they're doing. So as data scientists, we have to be aware of how the data is getting collected, and we have to be able to prepare that data so it's easier to use for us. So maybe they forgot to do it for a couple of minutes. Maybe they did it every 47 seconds, which is a really awkward time to measure that data. So we have to be aware of how do we aggregate and prepare and explore this data. For the second one, all we have is free text. one of the ideas I might have is, okay, well, let me see if I can cluster similar words. So here I have a cluster of words like injured, harm, hurting, spasm. So all of these words are indicating the type of pain this person is in. Over here, I have veteran, military, Vietnam. Words that are telling me the status, the veteran status of this person. So these are just ways of clustering like words. Again, to get a better idea of the structure of our data. So this is all about structure. Questions? Thoughts? Comments? 3, i.e. the fourth. Building and evaluating models. Now, this is where we're going to pretty much dive deep into this head first, starting next Monday. This week, we'll be focusing on how to explore and prepare data. Next week, we're going to be looking at how to actually assign machine learning models, how to apply other statistical models to our data. But there's 2 parts to this, building and evaluating. Both equally important. In fact, honestly, evaluating is as important, if not more important than building. Evaluating is this idea of, okay, I've built this thing. How good is it? How well does it work? How well can I predict neonatal infection? Can I only get 20% of them? Can I get 80% of them? 90% of them? Can I get 90% of this age? 80% of this other age range? I have to be able to know how well my model is doing. And what evaluation does is it allows me to iterate. It allows me to build better and better models. In the first example, I've listed some of the tools that we're going to be learning in this class. We can compare using a decision tree with something called logistic regression, which are 2 models for predicting yes or no questions, and we have to know which one is better. Why? How? For the second one, there is this model, again, which we'll be learning in this class, called the naive Bayes classifier. And it is one of the go-to models for text aggregation and classification. One of. So these are just 3 examples of models that we're going to be learning, and we're going to be learning the metrics that go along with them. How do we know how good my yes-no answer is doing? If I have a scale of 0 to 100, how do I recognize how good I'm doing? What if I don't have an answer that's yes or no? These are all questions and answers that we're going to be looking at. And finally, communication, which comes for you guys, especially towards the end of the class with your final project. Any model that you create for the good of society and for the world is useless if no one knows how to use it. If you create the most amazing program that predicts forward stock returns or can predict neonatal infection 72 hours in advance with 99.8% accuracy, but to run it, you have to run this C program, then you got to go down to the corner store, talk to a guy named Tito, tell him the wolf house at midnight, go drive you to his van, to another place. If it's too complicated, no one's going to want to use it, and it's more or less useless at that point. Communication is how you show what you've done to the world. And in the class, we're going to be talking about how to make a website to actually house our machine learning models. You're going to be using your GitHub as a way to communicate your results, and you're actually going to be coming up here and presenting to us your findings at the end of the class. So you will be working on communication in this class, as well as building an evaluation, exploring and preparing, identifying and collecting, and asking problems and questions. You will be doing all of this in this class, pretty much every day, or at least one of those. So for the first one, for example, you can create a custom dashboard, where the dashboard is enter 16 numbers here, and they can enter numbers. People can use keyboard. They enter the numbers, they hit enter, and then a big pop-up comes up that says 89% sure this child will develop infection. Simple enough. That works? That works. For the second one, a report and dashboard proof of concept. Import PDF, scanning, running. Again, 98% chance that this should be approved. I think it should be approved. It's got to be simple. It's got to be explainable, but it's got to be succinct, and it's got to be in-depth. You have to be able to say everything that you're doing as simple as possible, and we'll have a lot of practice. So what are some qualities of a good data scientist? We ask rational questions. Who are we? Why are we here? We ask rational questions. That sounds silly to say out loud, but you'd be surprised. Can I predict neonatal infection before it occurs? Yes or no? That is a very rational question. Can I predict this child's entrance into Harvard University from the age of 2 months? Go ahead and try, but that seems like an irrational question to me. But then again, that won't stop you from finding articles of people doing it out in the New York Times. So we have to be able to ask reasonable, rational questions. Understand the pros and cons of different techniques. We don't want to get stuck in Python for the rest of our lives. Even though this class is in Python, the skills that we're using can be transferred over to other languages. We don't want to get stuck in statistics. We don't want to get stuck in one problem again. We have to be able to understand the pros and cons of different techniques. And one of the nice quotes that I like to show, statisticians, like artists, have the bad habit of falling in love with their models. So what this means is, for example, if you love the linear regression, you think drawing a best fit line solves all of your problems, that is falling in love with your model. That is the idea of, well, if I turn this into a linear regression, then I'm pretty sure I'll get a good enough answer. And you keep doing that, and all of a sudden you have 20,000 lines in your life, and nothing to show for it, nothing to show. But you have to be able to understand, okay, a linear regression might work well here, but when it comes time for text, I'm going to have to work with an naive-based classifier. When it comes time for blank, I'm going to have to work with a decision tree, because I think it works a lot better in this case. So we have to be able to understand. And that comes with the evaluation part of the metrics and the models. That's the evaluation. How do we know, how do we compare? So we don't fall in love with one model. What a great photo. That's how I want, just communicates clearly. And sometimes I don't do that. But for the majority of the 6 hours that I have you, I communicate fairly clearly. And this is obviously part of the communication, the last step. Clearly can mean a lot of things to a lot of different people, but generally clearly is succinct, short, usually short, specific, and understandable. I can show you all day long the mechanisms of why linear regression actually works, or I can just draw a line and say, look at the line, it's pretty and it works. So there are many ways I can go about explaining to you a line of best fit. But as long as it's clear, I'm doing my job. And last but not least, we retain intellectual humility. I am not the smartest person in this room. I've said that before, and I'll say it again later on in this course. I'm not the smartest person in this room, because you all have some level of expertise that I can never fathom to have. Whether it's in physics, whether it's in finance, whether it's in shopping habits, whether it's in marketing data. There are many skills that all of you have that I just don't have because I don't have the time and effort to dive as deep as you have into something. So we must be able to retain intellectual humility. If I don't understand a medical problem in front of me, I will call one of my doctor friends. If I have a problem in Java, which I haven't done in years, I will call my friend who works at IBM, whose primarily the language they use is Java for IBM Watson. If I have a problem with math, I will call DJ Patel, my homeboy. Well, he doesn't know that yet, but I'll call DJ Patel. Okay, that is my brief introduction to data science. Are there any questions? Are there 45 minutes on the dot? Are there any questions before we actually jump right into exploring and comparing data using Pandas and Python? All right, let's get to it. Now, last time we worked with a variety of tools, IPython, notebooks, and Spider. Today, what we're going to be looking at is one Spider file. You'll find in your code the o3pandas.py. Does someone want to walk me through how to open Spider again? Remember, this is Spider. How do I open this software? There's that launcher, the Anaconda launcher icon that you downloaded in the beginning of the class. If you double click on the launcher, which is that green icon that should be put directly on your desktop, or if it's not, you can search for it. Let me show you. Stop. This thing right here, the launcher. If you double click that, you will have an option to open Spider. As always, if you're having trouble, please raise your hand and call over a TA. Now, when you have open Spider, take o3pandas.py and drag it right in, like drag it right in, and you will see all of this stuff appear right before your eyes. First question, Ramesh, can you read this in the back? A little too hard? Can you read it? A little bigger? That's fine. Why ask? Is this okay? People in the back, people in the front, is this all right to read? You have it in front of you as well, but I want to make sure that you can read what I'm doing. Danielle, what do you think? Can you read this?
Yeah.
What does this say? What does this say? Type drinks. Okay, good. Great. So I want to make sure. So, we're going to be running through this code file. In this code file, we will be looking at 3 different data sets. Now, time permitting, I'd love to go through the whole thing. However, what I want to do more than go through this is start on a lab after the break. The lab will test some of the Pandas skills that we're about to go over right now. So, Pandas is a data exploration tool. It is a tool for bringing in data and manipulating it and displaying it and visualizing it in a very succinct way. Last time we were using the CSV module, we were using the Dix reader, if you got that part in the homework. We were using all kinds of things to try to make sense of that drinks data. Well, now I'm going to import the same exact data using Pandas. And we're going to see the differences and similarities between them. So the first thing I'm going to do is I'm going to run lines 11, 12, and 13 by highlighting all of them, and on a Mac, Shift-Enter, on a Windows, Control-Enter. What you should see happen is on the right, you'll see all of your import statements. I've imported 3 things. I've imported Pandas, which is the name of the module. Why is it called Pandas? Someone called it Pandas one day. That's my story. Someone called it Pandas, and now it's called Pandas. And this as PD, all that means is, from now on, whenever I say PD, I mean Pandas. It's just an abbreviation. I could have called it anything I wanted. PD is a standard. PD is just, PD Pandas. So I will also import NumPy as NP. So anywhere in this code base where I use NP, I really mean NumPy. Do you remember what NumPy stands for? Numerical Python. That's what NumPy stands for. It's a numerical Python base. There's also a SciPy, scientific Python. And matplotlib.pyplot as PLT. So matplotlib is what? Who remembers? The graphing utility. And I'm just going to call it PLT. So anytime you see PLT, I'm not trying to say TLC, I'm trying to say PLT, which is my abbreviated form of my plotting utility. So I have 3 things: PD, Pandas, NP, NumPy, PLT, matplotlib. And I will say them throughout the course, throughout the session as they do it. First line of code. Line 21. I'm going to make a variable called drinks. Drinks is going to be PD, Pandas, dot read CSV. That sounds like a very useful function, doesn't it? Pandas dot read CSV, and look what I've given it. I've actually given it a URL. I gave it a URL, and if you put that URL into whatever browser you're using, what you'll actually get is, oh, I've hosted this CSV online. It's on the GitHub. I'm actually calling it directly from the web, which is one of the nice many features of Pandas, is you can call data directly from the web. So I'm going to run line 21. And assuming you're connected to the internet, there should be no errors. Nothing happened, except that I've created this object called drinks. What is drinks? Line 23 will tell me the type of drinks. And this, my friends, is the #1 used object in Pandas, and it's called the data frame. The data frame is essentially a representation of row-column structure in Pandas. Has anyone here ever used the language R before? You might be familiar then with the data frame from R. It is meant to be a replica, but better. So the data frame is a row-column structure. And remember in a CSV is essentially a row-column structure. I have rows separated by columns, and I have, rows separated by commas, and each comma tells me which column I'm in. It's like an Excel spreadsheet. Well, let's examine this data. So line 26, I'm just going to print drinks. So this is just drinks. And I see this. Whoa. When I do drinks, what it will do is it will show me the first 30 and the last 30 rows of the data set. Bless you. And if you scroll up, we're saying, oh, okay, well, I see that I have rows. I have a country column. I have a beer servings column. I have a spirit servings column. A wine servings column. Excuse me. This should be familiar to you, rather. This should be familiar. This is the same data set we were working with last time. Country, beer servings, spirit servings, wine servings, total liters of pure alcohol, and the continent. But this is kind of a lot, right? It's 30 of them is kind of a lot. Well, so what we can do is 27 drinks, which is the data frame, drinks.head will show me the first 5 columns, or 5 rows rather. Will show me the first 5 rows. So here we're looking at the first 5 rows of our data. We have Afghanistan, Albania, Algeria, Andorra, and Angola. First 5, and they're in alphabetical order. To get the last 5, there's another method called drinks.tail. Drinks.tail will give me the tail end of my data, the last 5 rows. Venezuela, Vietnam, Yemen, Zambia, Zimbabwe. Those are the last 5 rows in my data set. The point of head and tail is to get a very cursory look at my data. I'm just looking right now at the rows in the column structure. I can see how many columns are there. Country, beer servings, wine servings, spirit servings, total liters of pure alcohol, continent, right? There's 6. There are 6 columns in this data set. Okay, fair enough. I have the data. It's all loaded into memory. It's at my disposal in Python. What can I do? Line 29, drinks.describe. This one little tool, drinks.describe, that one line of code, will take every numerical column and give me base descriptive statistics of each one. Drinks.describe will tell me count, mean, standard deviation, min, 25th, 50th, 75th percentile of all of my numerical columns. In this case, that's wine servings, beer servings, spirit servings, and total servings of pure alcohol. For each one of those 4, I have how many there are, 193 of them. The mean, 106 beer servings, 80 spirit servings, 49 wine servings, 4 liters on average per person per year. So with that one line of code, we're already generating basic statistics. So if I were to ask you, could someone tell me the average beer consumption of a person in the world per year, what would you tell me? What is the average consumption, raise your hand, average consumption, Nick, what is the average consumption per person per year? Of beer. 106.16 servings of beer per person per year on average in the world. Line 30 is another method of data frames, .info. .info gives us a bit deeper, digs a bit deeper. When I do .info, it will tell me I have 193 entries, rows. I have 6 total columns, 6 columns. Country, which I have 193 not null objects. Beer servings, 193 not null ints, int 64. Does anyone know what 64 means? 64-bit. Beer servings, 193 not null integers. Spirit, same. Wine servings, same. Total liters, same. Continent, whoa. 170 not null objects. Why are there 23 continents not there? Let's keep that in our minds. Drinks.columns is a simple way to show us the columns. Country, remember the Unicode, the Unicode? We have country, beer servings, spirit servings, wine servings, total liters of pure alcohol, continent. So that one line shows us all of the columns in our data set, all 6 of them. And drinks.shape will tell us very concisely the number of rows and the number of columns. It will return to us a tuple, or tuple, I say tuple. A tuple where the first element is the number of rows, the second element is the number of columns. So, head, tail, describe, info, columns, shape. Between those 6 functions, we can get a basic look at our data with head and tail. We can describe some basic statistics using .describe. We can get some more in-depth info by what's null, what types of data that are in my data frame using .info. We can look at the column names using .columns, and we can easily get the shape, the rectangular shape, row columns. Any questions so far? So now this is easy. I can do this in Excel. What's the point of this? Well, first of all, tell me how long it would take you to find the mean of all these columns in Excel, and then versus one line of code here. Yes?
So with info, if there's like one object and a bunch of numbers, it'll say object, right?
Good question. Yes. So columns, like lists in Python, can hold any number of different things. So when it is not sure of all the mixes and matches, it will say object. That being said, strings are also represented as objects. So it won't say not null strings, it would also say not null objects. And that's just a factor of whoever wrote Pandas decided to not have string be its own. It's called an object. Okay, well, I'm still stuck on this. I'm sorry. I'm still stuck on the fact there's only 170 and the rest are 193. Because that's weird, right? That's weird. Luckily, line 35, if we do drinks.isNull, it will scan the whole data frame for every null, none, not there element, for any errors. And if you actually run 35, you'll first say, whoa, what's happening? Line 35 is a data frame, 193 rows and 6 columns. It is the same exact shape as our original data frame. However, every element is now either true or false. Strange, but not really. Here's what it's doing. It's going through every single cell, 193 times 6 cells, all of them, and if that cell is null, i.e. bad, it will say true, i.e. it is null. If it's fine, if there's a number, there's a string, there's something there, it will say false. As in it's not null, it's fine, don't worry about it. The trues are the ones we care about. Okay, that's fine, but Sinan, that's hard to look at. Again, this is, what if I have 1,000,000 rows and 17 columns? That's fair. Line 36. Drinks.isNull, this data frame, .sum. That seems too simple to be true. But it is too simple. It is good. It's good. It works. I lost myself in words. What we are looking at is the count of null objects per column. But why did sum work? Those were all trues and falses. How do you add trues and falses? Well, I'm glad you were asked. In Python, true and false is identical to 1 and 0, at least to the system's kernel. True and false is the same thing as 1 and 0. And if you don't believe me, I'm going to go into my console here, on the right, here at the top. I'm going to write 1 plus 1, 2. Fine. I did math in college. True plus true is also 2. You can add booleans together. They are identical to 1s and 0s. I could do true plus 6. It's 7. True is just a 1. A false is a 0. I could do false minus true plus 5. And what will this give me? 4. So what happened was drinks.is null made a bunch. In my row column structure, I took a bunch of trues and falses. That was a pretty F. True, true, true. And it gave me the sum of each column. So the sum here was 3, the sum here is 1, and the sum here is 2. Why does that matter? Because in is null, line 35, true and false is identical to saying bad and good. If it's true, it's null, it's bad, we have to take care of it. If it's false, it's fine, it's not null, don't worry about it. So when you add up all the trues and falses, the resulting integer is the number of bad things. Because it took all the trues, added them together, 1 plus 1 plus 1 plus 1 plus 1, and it eventually gave us that there were no trues in country, which means they were all good. There were no trues in beer servings, all good. Spirit, all good. Wine, all good. Totalers, all good. There are 23 null objects in continent. That's the error. Interesting. There are 23 null objects in continent. Well, that's fine, I guess. Why don't we just get rid of them? Line 39, drinks.dropNA. Drop NA will do exactly as it's told and drop all of the rows with non-applicable or null or none in it. So when you do drinks.dropNA, notice how many rows I have. 170. It took the original 193 rows, it took out all of the 23 with the null continents. This is what we have instead. 170 rows. We're done, right? We solved the problem. We got rid of all the nulls. Yes?
Could we have seen what it was?
Why would you want to?
I'm just curious.
I'm curious too. What did I just drop? That's a good question. Thank you for asking. What did I just drop from the data frame? Does no one already question that? I just dropped like 10-15% of my data and no one said anything about it. Let's look at what I just dropped. Because that can't be right. Well, they're all in continent, right? Okay. Let's look at drinks. This is my 193 rows, unfiltered. This is my data. Right here in my continent, I have AS, EU, AF. Okay, what does AF stand for? Say it again. Asia, Europe. What is AF? Europe, Africa, missing. What is SA? South America. EU, what is OC? Oceania. Good. Sorry to burst your bubble. Pluto's not a planet. Australia is not a continent. Oceania is a continent. Australia is a country in Oceania. Europe, missing. AS, missing. EU, missing. Does anyone notice anything weird? Is there a continent that you're not seeing pop up? Which one? You're living in it. North America has yet to pop. North America has yet to pop up in this data set. Isn't that weird? I wonder why. Well, if you open drinks.csv, which I have other things open, if you open drinks.csv, and you kind of look at that column in an Excel spreadsheet, again, I'm just looking at it here, NA is North America. What do you think happened? Say it louder. It thought it was not applicable. Python saw NA and said, oh, not there, not applicable. And it turned all of North American countries into not there. All 23 of them in the data set. That's a problem. That is a big problem. See, as data scientists, we just figured that out. And yes, we looked at Excel. That's fine. We turned to Excel. We did some literal looking. We looked at the data. This is weird for whoever's watching this. We looked at the data very intensely, and we figured out, North America's missing. And then we came to the conclusion that, all of those NAs, it probably thought were non-applicable. And that's exactly what happened. That is exactly what happened. So, first of all, thank you for pointing out why did you just drop 23 rows and no one batted an eyelash. And thank you for helping us figure out that, yes, it all turned into all the North American countries were just gone. We were about to do an analysis on a data set with no North American countries. That doesn't sound very sound for a World Health Organization report. So instead of dropping NA, instead of getting rid of them, let's replace all those missing values. Line 40 will fill NA. We'll replace all of the non-applicables, all of the nones, all of the bad stuff, with the value string NA. And this is how I'm going to fix that. Line 40. Look at that. Now in my column, instead of NaN, you know what NaN stands for? Not a number. See, nulls come in a lot of shapes and forms. Null, none, not a number, non-applicable. They come in many shapes and forms. Not a number is one of them. But now it's not a number. It's NA. It's North America, which is exactly what we wanted it to be. Now, line 43 will read in the data again, but you'll also notice, read CSV, it's the same exact URL, but I've added an optional parameter. I've added an optional parameter called NA filter, and I said it's false. Does anyone want to guess, or an educated guess, what NA filter equals false will do? Don't say it. Don't think about it, Pandas. Don't worry about it. I know what I'm doing. Don't try to filter out the NAs. Because what Python did, it's not the smartest thing in the world. It saw NA and said, non-applicable, fine. By setting NA filter to false, we're saying, don't try to filter for us. Let us handle that. So I've rendered the same exact data from the same exact source, except now I've told Panda to don't worry about filtering. Let me worry about that. So now when we do that is null sum, nothing is missing. Great. All of my comments are accounted for. I have zeros all across the board. I have no missing values. This is every data scientist's dream. Please, are there any questions at this time as to what we've done so far? Yes.
Why did it say NaN?
Good question. Like I said, null, bad values come in many shapes and sizes. NaN is just one of them. They could also be written as none, as you're probably more familiar with in Python, because they none. NaN stands for not a number. Another one is called inf. Inf stands for infinity. If you try to do 1 divided by 0, you'll also get a bad thing. And it's called inf. Also missing. So NaN is just one flavor of that. The PhD in statistics knows, 1 divided by 0 is usually not a good thing. Correct?
Usually no.
Usually no. Usually no. Okay. Fair enough. So far, so good. We have now fixed the error in our database, in our data frame. We have no missing values. Let's get down to business. I want to look at the continent column. Just a continent. To call a column in specific, I will use square bracket notation, just like we would in a dictionary. Isn't that weird? It's not weird. Because here's why. A Pandas data frame, well, someone made it, right? Someone made a data frame. Like a person sat down and wrote it. A Pandas data frame is a dictionary. A dictionary, where the key is the same as, where the key is the same as a, oh my god, I'm blanking. Index, thank you. And the value is a column. You can also think of this as you can particularly think of the column name. And this you can think of as a list, or the alternative to a list in Pandas is what he calls a series. So we have data frames and series as the main two types of things. The data frame is the row column. A series is like a list. It's like a one-dimensional string of things. So when I say drinks continent, it looks like I'm using a dictionary, because that's exactly what I'm doing. I'm calling a dictionary where the key is the column name and the value is the column. So when I call drinks continent, I'm getting back the entire continent column. So now I've singled out the entire column. I'm not looking at country, I'm not looking at beer servings, I'm looking at the continent, period. There is an alternative notation to this. Line 48, drinks dot continent, is another way of doing the same exact thing. So you might see it written in different ways on the internet, using the dictionary notation and using more of a functional notation. They both do the same thing. Why have both? If your column name has spaces in it, you can't use the dot notation. If you have spaces, you must use the dictionary notation. In fact, I will likely use the dictionary notation 95% of the time because it never not works. Sometimes the dot notation won't work, but this notation will never not work. So I will likely use the dictionary definition or notation for the majority of the course. Yes?
What if you have a variable called consonants?
That is something else. That's why I would use the dictionary. That's a great point. What if I had continent, and what that was a string that was beer servings? Just to add, just more confusion to everything. Now when I do drinks.continent, it will give me the continent. And if I do drinks continent, it will give me beer servings. So, if you're going to make variables that are confusing in nature, A, I suggest you don't. But B, if you stick to the dictionary notation, you will always be aware of what you're doing. Because if you have a variable called continent and it's a string beer servings, and you throw it into the data frame, it will look at the beer servings. So I generally recommend you stick to the dictionary notation. I'm showing you the functional one because it is used, people use it, so I think it's useful to see it. So that when you see it out in the wild, you're not like, hey, what is this? I don't know what they're doing. So drinks, learning opportunity. What is drinks? What type is drinks? Someone want to tell me? Raise your hand, Tom. What type is drinks? What type is drinks? Drinks is unfortunately not a list. It is, I'll give you a hint, it is a Pandas specific type. There's two types of Pandas objects.
Oh, series.
The whole row column structure is not the series, it's the data frame. Drinks itself, type drinks is a data frame. The type of drinks.continent, the column, that's a series. Series, think of a series as being equivalent to a list. They're both one-dimensional, just a list of objects. Whereas the data frame is like a frame. It's like a rectangular frame of data. It has rows and columns. So data frames are rectangular. Rectangles have rows and columns. Series is just like a time series. Something happens in series. It is one by one by one like a list. So drinks is a data frame. Drinks.continent is a series. Yes?
Those answers look redundant, like frame.data frame and series.series. Is there anything?
Yeah, so whoever wrote Pandas, there are other types that are not just data frames and series. So whoever wrote Pandas decided that, okay, I'm going to have a frame object, and a type of frame is a data frame. There are other types of frames that he also created, but we're not going to use them. So this, you're right, it seems totally redundant, But to him, or team, her, I don't know who wrote it. I actually don't know who wrote Pandas. I'm not gonna lie. They have the pandas, then they have their core objects. One of the core objects is a frame. One of the types of frames is a data frame. So it seems redundant at first, and to them, okay, pandas, one of the core objects is a series, and the most basic type of series is just going to be called a series. And there are other types of series. There is a time series, which is another type of series that they created. So that's why it seems a little redundant in nature. Does that make sense? Okay. I'll watch the time. Ooh, almost break time. Almost there, guys. Don't worry. Remember describe? What did describe do? Gives you basic descriptive statistics of all of the numerical columns. But what is continent?
Series.
It is a series, absolutely. What type of things are inside of continent? Are they numbers?
Numbers.
No, they're objects, otherwise known as strings to us. So I can call describe on it, and it will also give me base statistics. But to pandas, base statistics to strings are how many there are, how many unique ones, the most mentioned one, and how often the most mentioned one is mentioned. So there's 193, good. There are 6 unique ones, Europe, North America, South America, Asia, Oceania. South America, thank you. South America. Africa is the most common, and Africa occurs 53 times. That's what happens when we call describe on what's called a categorical. This is a categorical, not quantitative, it's qualitative. It's not numbers, it's strings, it's categories of things. Because what is the mean of the continents column? What is the mean?
Some value.
Of continents? Doesn't exist. Because continents are strings. How are you going to add up all the strings and divide by 193? There is no mean of column. There is no standard deviation. There is no percentiles. These are the basic things you can tell about a bunch of strings. How many there are, how many unique ones, which one's the most often occurring, and how often that thing occurs. Basic. There's also something called value counts. This is probably one of the nicest things to do for a categorical column. Drinks.continent.value counts will give me the count of the values in continents. You know that works? So there's 53 Africas, 45 Europes, 44 Asias, 23 North Americas, 16 Oceanias, and 12 South Americas in my 193 row data frame. That's the breakdown of all of the continents. So value counts will literally give me a count of all of the unique values in my continents column. And again, this is instead of doing the mean standard deviation because we can't do that for strings. So now we're learning how to do basic descriptive statistics for not only quantitative numbers, floats, integers, but also for qualitative strings, categories, continents, things like that. We can select multiple columns. Drinks, country, beer servings. Note the double square bracket. And I want to explain the double square bracket. Now, it's not just Pandas notation, double square bracket. There's actually 2 uses of the square bracket. Now let's break it down. We have drinks, which is what type again? Data frame, our most favorite thing in the world. Drinks is a data frame. How do we call a column from a data frame? Like a dictionary. Okay, but what if I want to call more than one thing? How in Python do we hold more than one thing? Why? What is that thing called? It's an L word. List. Let's, instead of giving it a string, let's give it a list. How do we make lists? Square brackets. So this isn't some weird double square bracket notation. This is us putting a list inside of the square brackets for getting columns. So in here we have column 1 and column 2. And when we do that, when we give a list to the data frame, we'll get back another data frame, but look how many rows we have. 193, all of them. But how many columns do we have? Just 2. Which columns? Country and beer servings. To make that even clearer, I'm going to make a list called My Calls. My Calls is a list of two things. The first thing in My Calls is a string called country. The second thing in My Calls is a string called beer servings. And then in this next line, I'm going to do drinks, my data frame. Bracket, I'm going to get columns from it, and then I'm just going to literally put in that list I just made. And I will get the same exact thing. So this is literally putting a list inside of the dictionary get of a data frame. So it's not some weird double square bracket. It's just one square bracket is for a dictionary notation, the other square bracket is for a list. That's it. Let's make a new column. Let's make a new column. Line 71 will make a brand new column. How do I make a column? I use the call notation as if I was getting that column. I'm going to say drinks total servings. Total servings does not exist. That's not a column. I'm about to make it. Total servings, I want it to be the beer servings plus the wine servings plus the spirit servings, right? Because the total number of servings of alcohol, you just add them all up. That makes sense. What's really nice about data frames is that when you add columns together, well, let me ask you this. What happens when you add two lists together? Like a Python normal list. Someone know? What happens if I add two lists together? Let's find out. Let's have A be 1 and 2. Fair enough. B is 3 and 4. Does anyone know what A, bless you, plus B is? 1, 2, 3, 4. It puts them together. It concatenates them. What it doesn't do is add them element-wise. Because I heard, I think I heard, someone said, well, it's going to be 4, 6. Because 1 plus 3, the first element added together is 4. And 2 plus 4, the second element added together is 6. Right? 4, 6. But that's not how base Python works. But in Pandas, that is how it works. A1 is this new variable I'm creating. It's going to be, I'm going to create a Pandas series with A. So now A1 is 1 and 2, but now it looks all fancy with the int64. Now it's a Pandas series. And yeah, I just made a series based on a base Python list. You can do that. B1 will be a Pandas series with the elements of B. So now it's 3, 4. Note the 0, 1, that's just showing you the index. The 0 index, the 1 index, it's just showing you the index on the side. So now I have this 2 series. If I do A1 plus B1, it does it element-wise. This is 4, 6. And when we're doing statistics in data science, when we want to add 2 columns together, we're not trying to make one giant list of beer servings and then wine servings and then spirit servings. No, we're trying to add them element-wise. So add the first country's beer plus wine plus spirit. Second country's beer plus wine plus spirit. We're trying to add the columns element-wise. So line 71 does just that. Total servings is going to be drinks.beer servings, which is a column, a series, plus drinks.spirit servings, which is another column, another series, plus drinks.wine servings, another column, another series. So I will run line 71. Note nothing happened, nothing outputted to us. But to check that it actually worked, we can do that dot head again to get the first 5 rows. And now we can see, oh, look at that. Country, beer servings, spirit servings, wine servings, total liters of pure alcohol, continent, total servings. Now I have 7 columns. So we just created a new column by adding element-wise 3 of them. Now this will become very useful to you. When you have a column of Fahrenheit and you want to turn into a column of centigrade, you can just do element-wise a function that turns Fahrenheit into centigrade. And we'll do examples of similar things. So it's nice that we can do things element-wise in Pandas. We can apply a function to every single element, or we can add two columns together to make a new column. We can divide, subtract columns to make new columns. So far, we've done head, tail, describe. We've gotten a single column. We've gotten multiple columns. We've added a new column. Let's take a break. And when we come back, we're going to start to filter through the rows. So let's take a 15-minute break at 7:55 by my watch. We'll come back at 8:10, and we'll start at 8:10.